It probably doesn't make sense to wait longer, right? So that's what we get today in terms of attendance. I hope you had a great weekend and enjoyed the winter and snow in Salt Lake City. I hope you go skiing and whatever you like doing, maybe snowshoeing or whatnot. So let me quickly just ask you. So you did the quiz, okay, right? Did you have any problems with the quiz, or everything was fine? I mean, not in terms of content. Content was like kind of easy, right? So you read the book, you answer the questions. Some people complain that they are slightly ambiguous. I agree. I mean, I kind of disagree, but I mean, like any question is ambiguous unless you spend like several hours explaining what you mean. I would say it doesn't matter that much at this point, because you will have a ton of quizzes, and quizzes will become way more concrete. It will be like, build a page table and put this entry, a concrete number. So it will be harder to it just the very first quiz was hard to, there was nothing to ask really. Question.
Just would it be possible for the time to be lengthened? Like we can have it timed for 15 minutes to take it, but to retake it so we can ask questions about the ambiguous questions.
Well, the thing with those quizzes, the idea was to we usually set a fixed time. In the past, at least that's what we were doing. The reason was to force you to spend some reasonable amount of time reading the class materials for the week, watching the lectures, participating in classes, right? And if I give you more time, you say, look, I will be asking questions as I go through the quiz. So that's the reason why it's like fixed lengths. So, but you say, again, I wouldn't worry too much. So I don't know how to address it really. If it's a timed quiz, which like the goal is to force you to work up front or participate in class, in the lecture, in the room, right? I mean, we can figure out different strategies for how to increase participation, but the quizzes is my strategy at the moment. What I wanted to say. So I don't see an easy answer. But if I screw up the question completely, which happened in the past, then you just say, look, you were wrong, and you say, yeah, this question is off the table. That's what usually happens. Or we grade it super lenient. Yeah, another question.
Could we have an extra question that's just like pre-responses? Type in like, I answered this question assuming these things.
Right.
Yeah.
Then we have to grade. That's the problem. So the quizzes are 90% of the questions will be designed in such a manner that we can avoid grading. We have some horrible situations with TAs. It's very hard to find people for this class, like qualified people. That's why, and again, quiz is nothing. We might have some design exercises where it will be a free response, and then you can, it will exercise your ability to navigate the open space. Quizzes are more like, I read the book, I can prove it. That's sort of thing. And a couple of people mentioned that I should add a link to Gradescope and maybe integrate it as a module. I will try. I forgot. Sorry about it. I will. And I forgot, did I even send the link to the Gradescope? I think it was on the web page somewhere, right? And the second thing, what was there? I should start adding all the homeworks to the Canvas so you have them on your calendar. And I forgot that as well. So I will start doing that. So it will, if you use Canvas as in all your classes, then you will have the deadlines. Okay, so and now, okay, but essentially it happened, so it's not bad. So everything kind of seems to work logistically, and we will have a first homework assigned this week. It was originally on the website as assigned as of today. We need a little bit more time to figure out how to do it. So maybe today or tomorrow it will be assigned. I will send an explicit notification on Canvas. Okay, any other questions? Yeah.
Just curious, what's the topic of the person?
Topic was make files, essentially how to build simple Unix programs. So you can do it in shell, and just because because the kernel itself will be built with make files, and it will help you to kind of understand what's going on. It's kind of more of a lab, which you read a little bit what's inside the make file and why it works this way. So it shouldn't be super hard, but it's usually takes a little bit of time. Okay, so then our topic today is actually quite interesting as usual. So let's quickly recap. So last time, or for the last week, right? So we were talking about this new piece of software, which we called an operating system, or I sometimes call it operating system kernel, or just the kernel, that yellow piece, which I draw it at the bottom, because typically you draw the hierarchy, like the physical hardware at the bottom, and then the first layer, which runs closest to the hardware, and then the upper layers, typically applications, right? But sometimes there is something in between, like device drivers and some operating systems. And I was trying to explain you what operating systems are typically doing. And here's a quick recap. So they said, okay, they're kind of like allow you to share a single piece of physical hardware, like a CPU or physical memory, across multiple applications. And it's done by switching from one process to another, switching so fast that you, as a human, don't even notice in most cases. If it's your business to make money on quick transactions or something like that, or do something really, really latency sensitive, then you will notice, right? So your whatever profits or user, like the latency which user perceive will go, latency will go up, profits will go down. So that matters in the end, but in many cases, at least originally, it doesn't matter. And we also talked that we have this layer of device drivers, which essentially provide a single unified interface, and something simple like send and receive. And internally inside the device drivers, a lot happens, like you configure the ring buffers, which allow the hardware device to access the packets which you're trying to send. You talk to the device, stuff like that. We'll talk a little bit later, right? So that's also what operating systems are doing. And you could also can think about them as libraries which provide certain functionality. This functionality will be access to files, access to network, creating processes or programs of execution, stuff like that, right? And they also, operating system also enforces some security guarantees, so essentially isolation between processes, right? And some controlled ways in which processes can communicate between each other and to the operating system kernel, right? So that's a recap. And I said, okay, this is a typical architectural diagram of a typical kernel which we use today, something what evolved out of Unix operating systems. And there is this single piece which is called a kernel. It has those mechanisms to create files, communicate on a network, some mechanism to manage physical memory and provide this virtual memory interface on top. Some mechanism which is called a scheduler, which switches between processes and enforces fairness to make sure that each process has a fair fraction of a CPU. And on top of that, we run multiple applications, right? So here we run a shell and an Apache web server, right? Two processes, for example, and operating system switches between them, right, with some interval. And the topic of our lecture today and possibly on Thursday is to understand what is this interface. So what kind of interface operating system provides to the programs so they can do what they want, right? And typically this interface is implemented as a collection of system calls. So system calls think of them as library functions. They're just a little bit more protected, or I would say quite a bit more protected in such a manner that a malicious program which you download from an unknown site cannot access the kernel and essentially break the isolation guarantees which the kernel provides, right? But in many other ways, you can think of them as library functions, right? And there will be a tiny layer here, which we will understand later. On modern Unix machines, it's implemented inside a library, which is called libc. And on x86, there will be like a tiny layer of code, which we will understand, which helps you to invoke those functions, kind of like invoke functions of a kernel. But most of our work today is to understand what these functions are. Essentially, what is this interface? What we can consider useful and at the same time minimal, because growing this interface to be large is also it's a security problem, because you have to ensure that those functions don't break the invariance which you want but also, you know, there is certain elegance and certain performance optimizations are possible if this interface is small, right? So essentially, system calls, right? As I say, it's the mechanism to communicate with the kernel. There is no other way to essentially ask kernel to do anything. So you always have to invoke a system call, right? And they implement the interface of the operating system. Okay, so we're not going to do it today, but just as a heads up. So at a high level, this is how it works. So if you're running your Apache or shell application here, you have some user memory, which is a heap. You have this dark region, which is a stack. And we will, in the future lectures, I will in details explain what these regions are and how they are maintained by the operating system. But you probably have heard those terms. So like heap is something allocated dynamically with a new operator or with a malloc. Stack is managed by the operating system to implement recursive invocation of functions, right? But or the language runtime. No one really knows what it is, but everyone knows that it's there, right? But we all understand what it is. And the way to invoke a function in a kernel is to actually invoke an interrupt. There are multiple mechanisms, but in the past, this was the dominant mechanism. Essentially, we will talk about how interrupts work, but I mentioned that interrupts are used to by the devices to interrupt execution of a kernel, by, for example, a timer, right? I said it last week. But it's also used by the operating system to expose its interface to the user applications, right? So literally, user code, when invoke this assembly int instruction, providing the number of a system call, and it's x80 on Linux, I think it's x40 on x86, it doesn't matter, it's just an agreement, it's just a number which operating system and application libraries choose. And then this essentially triggers an interrupt. Hardware saves the state of the user program, goes through something what is called an interrupt descriptor table. Don't worry about this too much. We will go in details and explore how it works. And then it allows you to essentially invoke a handler for this interrupt. And from there, you start executing the function of a kernel. So for example, like opening a file. But the mechanism is like that. So it's not just a function invocation. Why do you think it's done this way? Why do we use this interrupt mechanism? Anyone? I'm sure some people should know. Security. Okay, so what is security here?
The processes should not access the kernel code. Any random process should not have a privilege to access the code.
Well, but we do access the code here, the kernel code. In the end, you start executing kernel code here, right?
Yeah, but it should have some privilege level as to what kind of process is it or the kernel level or.
So if I, for example, say something like call, replace this assembly instruction int with a call instruction, which implements a function invocation. What can go wrong? What's anyone? Well, there's a couple of things which, and again, my goal here is to say, okay, here's a problem, and maybe you don't understand why it works this way. I cannot fully explain it today because it will take too much time. I will explain it later. Partially, you're right. So in general, these two memories, this yellow and green and blue, so this green and blue is memory of a process. So let's say it's a one memory region. Instructions which read and write memory here, like for example, move instruction, they can access this memory, but cannot access memory of a kernel because there is a protection mechanism in place which triggers a page fault or a protection violation, right? And then the kernel says, okay, you're trying to read or write my memory, clearly you try to break something, right? So even executing a function with this call mechanism, function foo, for example, inside the kernel is not allowed because of the protection guarantee, right? So this is the only way to kind of transfer the execution from there is a concept of privilege level, and user application run at privilege level 3, and kernel runs at privilege level 0. And that's the way to do it. But the real problem is yet another one. So this entry here in this interrupt descriptor table allows the kernel to configure the entry point. So even if you wouldn't have those protection mechanisms or would build them differently, the real goal here is to make sure that the user code can enter the kernel only through a well-defined entry point. And why? Because the first thing the kernel will do here is to do security checks, essentially ensure that the kernel, if the user says, okay, please write this buffer or read into this buffer, the buffer actually belongs to the user memory, not to the kernel, and the kernel isn't overwriting itself, right? So think of it as a security checkpoint, if you like, at the airport. So you can only enter the terminal through this entry point, and you will get inspected there. So that's the human analogy of what's going on here in the kernel. Because otherwise you can slightly change the entry here. Instead of foo, you can send maybe foo plus 20 and land past those security checks, right? So, and this is not allowed. That's the mechanism to enforce it. And we will talk about how interrupts are built and implemented by the kernel.
Why is the kernel memory space even not with the virtual memory space of the buffer? Why doesn't it work so well?
That's a great question. So, and it's not always mapped. And in fact, it's not mapped today. And if I ask you a question, why? Who knows? Anyone was in my, what is it, principles, computer organization class? And I scared people so bad that no one joined this class. Okay, maybe you know. Yeah, exactly. It's a specter. Or mostly meltdown attack. So there is a defense. Okay, first, why is it mapped? Because it's faster this way. Because if you go through this interrupt descriptor table mechanism to drop into the kernel, you don't have to switch the page table. The user memory is already mapped. And if the user program tries to pass some arguments like a buffer, maybe it's a packet or a write into a file, this buffer is already available. So you don't have to switch the page table. Again, I will talk a little bit about it, not a little bit, a lot about it later. Right now, you don't have to understand it, right? But then later on, there was this side channel attack, which is called meltdown, which allowed users to bypass, to exploit the speculative execution in the CPU, essentially. And it's nice, like if you don't know what it is, maybe we'll spend a lecture and I will explain what it is. How many people understand meltdown? Some people, like a couple of confident hands and a lot of, okay, we'll talk about it towards the end of the class. It's worth understanding. It's like not understanding, what is it, side channel attacks is kind of a failure today, unfortunately, just because they're so pervasive. And so right now, kernel is not mapped. And what you do then, you drop into the kernel and then you switch the page table and then the user memory becomes mapped. So it's called, what is it called? What's the defense? Okay, what? Kernel? Who can tell me? I forgot. KPTI? No. Kernel page table isolation. So this is a current defense, which essentially on the CPUs, which are not protected against meltdown in hardware, you have to use this technique and essentially make sure that this memory is not mapped. The yellow memory is not, the green memory and the yellow memory live on different page tables. Okay, enough of detours, although I appreciate the question. Okay, so system calls. And if I ask you the question, okay, we kind of got it. So the running system should provide the interface. If I ask you what system calls do we need? Give me a design plan. So which ones do we need or want to be implemented?
Want everything related to like the file system, so hopefully reading, writing files.
Exactly, files. Like opening, reading, creating directories, deleting them, stuff like that. What else? Reading input. Well, in Unix systems, everything is all input, I mean, to a degree and in the past, but at least in this system, which we discussed today, everything, all input is behind a file. It was kind of powerful until it broke with like GPUs and different devices, which have funky interfaces, which you cannot abstract with a file. So console, network has a slightly different set of system calls, but files, console, and pipes are behind a file. And we'll talk about it today. More hands and more system calls. But you're right, so input is kind of behind the files as well here. IO, yeah.
A process synchronization.
synchronization. That's a good thing. And I cannot type apparently this. You're right. Synchronization is a little bit interesting because I don't think this kernel which we discuss in this class provides synchronization mechanism, but in general, you're right, and it will be probably part of your homework to implement those synchronization mechanisms, extend the kernel with those synchronization mechanisms. So a hand which I never seen. Yeah, go ahead. Interrupt calls, but wait, interrupts are kind of like a hardware mechanism, which, why would you call an interrupt? Tell me, give me an example from an application. Why would you think it's needed?
Aren't there like anti-cheat systems that a lot of games use that basically run interrupts if they have programs?
Oh, say this again, anti-cheat system, which
Might be wrong, but I think there's multiple versions of like anti-cheat software that run as kernel code and will basically interrupt the program if it detects another program running. Which I think leads to some.
You mean like anti-cheat systems to implement DRM, stuff like that, digital rights management, or something else? What cheating you're trying to defend against?
I think it's, I don't know exactly how they work in those blocks, but I think it's to make sure you're not running any malicious software, especially with like.
No, like antivirus software, for example, might monitor your, might inspect the content of the process, for example, inspected memory and match signatures with original software, might inspect. Some attacks allow you to build Turing-complete computations on the stack called return-oriented programming, right? It's a little harder to inspect, or you can monitor system calls saying, okay, are you doing what you're supposed to do? Or you suddenly started writing files, which you don't have to read, right? That's usually implemented as kind of a mechanism which somehow monitors the execution, but I don't think there is like a specific, there might be some specific extensions which provide specific introspection functionality, but I wouldn't classify it as the core OS interface. Maybe more.
So basically, when I send some processes in the foreground or the background, or like when I send them stop signal or something like that.
Kind of like kill, right? And in general, like I kind of like that you started from sending processes to background, but you need to really create processes, right? So you need system calls to manage processes. So you have to essentially be able to create them. Revealed accidentally, but anyway, you have to essentially create a process and terminate it, right? And maybe manage it, like give it a priority. It's not in this kernel, but in some other kernels. But essentially, here's the list, right? So, and the list is not that big if you really want to keep it simple and small. I'll take a question. So you have system calls to essentially create, exit, terminate a process. This is kill. And maybe if you created a child process, wait on it to finish because you want to know that it's done and you can get some result back. You need interfaces to manage memory, so specifically allocate and deallocate memory. You need to manage folders and files, opening, reading, writing, closing, creating directories. You need mechanisms for at least some inter-process communication, right? So it can be a shared memory, like you can map a region of memory in both processes and start building like a communication mechanism on top. Or in earlier versions of these systems, the mechanism was called a pipe. So it's kind of like a buffer which allows you to write, which allows you one process to write a buffer into a buffer, and another process can read from that buffer, right? So, and this is kind of the closest we get to synchronization mechanisms in this kernel. But in other modern kernels like real full-featured Linuxes, there are some additional synchronization mechanisms which allow you to synchronize threads. x86 doesn't have threads, so you don't have to synchronize much here. So this is enough. There was a question.
Yeah. Isn't the pipe just sort of like an extension of files, more or less, though? Or is that like its own?
No, you will see today pipes are slightly different. So it's really just a buffer into which you can write and you can read. And they hide themselves behind files, because you can create a pipe, then you can read and write through the same system call which reads and writes files. And this is like continuation of that paradigm that everything is a file. And it used to work for a while until it got too complicated and not everything fitted that paradigm. But that was in this x86 kernel, everything is a file, really. Okay, so like it's kind of natural, right? You say, well, maybe I don't want to do anything else. And I will show you that this is powerful enough subset that you can run a lot of applications which you know. So here we don't have anything related to graphical user interface because this early Unixes, they didn't have really graphical screens, right? But besides that, everything else is kind of possible. And this set of system calls, which we will cover today, is designed to support this program, which is called the shell, right? And you've seen me running it, and I have a screenshot here, this program, which, like, for example, here I say ls is a command which lists all files in a directory, and it prints me all names of the files, right? So it's a source tree of the x86 operating system, right? And that's the program, right? And you say, okay, one logical question is why? Why is it designed around why do we design everything around the shell? Or why it was designed around the shell? Who can guess?
So there's an interface.
Shell is an interface, right? But not today. Today we have this wonderful, different devices which can interact with the machine. But back in the days, that was your interface. That was your machine. And your interface didn't even have a screen. It had a printer, right? So essentially, this is a Ken Thompson and Dennis Ritchie standing. They are working together on this PDP-11 around 1917, probably programming a kernel, which is very, very similar to the kernel we're covering in this class, right? And the guy here, for example, types ls, and he gets back the result printed on a sheet of paper. They literally didn't have a screen first. And you say, okay, then it kind of makes sense. I type ls and it shows up. Imagine file editing. It was possible, but it was a pain. So because, and later on this is the first terminal, which is called DEC L836. I never had chance to work with that, unfortunately, only seen it in a museum. Later on, this is the first design device which had a screen. It doesn't have a CPU. It actually dials over the phone to a machine which runs Unix. This thing you have at home, and because machines were so expensive that there was one machine and hundreds of users, but it's still a very, very already looks like a real modern thing. So it has a keyboard, it has a screen, and if you type ls here, it will show you on the screen, but there is no computer here, just enough hardware to make a phone call and essentially route this enough, those letters back and forth between the real machine and your terminal at home, right? So this is essentially DEC VT100, which appeared in 1980, roughly, right? But kind of, you see, I kind of tried to convince you that shell, this weird screen which I use here on my machine as well, makes sense. It's surprising. It's still very, very ergonomic for the things which I'm doing on my daily basis. So not everything, obviously. So, but a lot can be done faster than with a different graphical user interface. You will be surprised if you ever start using it. But anyway, so early system call interfaces and this kernel which we're covering was designed to support a shell, right? So here's so what is a shell? Shell is a program, right? Actually cover it on the next screen. And I wanted to ask you what shell is, but I told you already. So it's a program which operating system starts for every user. When you, for example, you log in through the terminal, which I just showed, you dial a number and you have to prove that you're a specific user, like Anton, for example. You type a password and the operating system creates a shell for you, right? And then you can type commands. So shell itself outputs this command prompt saying that it's ready to take a new command, because sometimes if I type ls and I have millions of files, ls will run forever. And if I type another command, shell might take it, right? But ideally, it shouldn't be designed to take a command until it finished executing the previous one. But essentially, that's for the user as well to know that the shell is done running stuff. That's the command which you type. Or sometimes you type a command like word count WC and provide some additional arguments. -L says count all the lines instead of words, for example, and you say in a file ls.c, right? And it will count you number of lines 85 in ls.c file. So that's how you interact with the system. Back then, there was no mouse, no interactive screens that came out later, but that was still powerful enough to run a lot of stuff. So shell, as I was saying, is a normal process. It's started by the operating system for each user, or sometimes a user can start multiple shells as well if she wants so. And in x86, shell starts when the kernel boots, essentially. There is no authentication, no logging in, just shell is immediately provided. And then shell interacts with the kernel through the system calls, and it allows you to create other processes. So for example, this WC is yet another process. It's not shell. It just, if you think about it, shell is kind of like a tiny language interpreter, kind of like Python. But back in the days, right, which would also make sense, you know, like I often start Python to do some computations just because it's faster and more powerful than just using a calculator, right? And so those people says, okay, look, you have some kind of a programmability in place. You can start new programs. We don't know which programs you will have, but they will produce some results on the screen or on the console or on their standard output, which you can redirect, and we'll talk about it in a second. And then you can combine them and do certain interesting things, right? Okay, we got this shell, right? So, but again, just let's go through this example. So when I type WC with some arguments, -L, ls.c, this is a shell, and you will have homework asking you to build a shell. So that's makes sense to kind of pay attention what's going on. Shell itself interprets what happens. So shell gets a string, right? You have to understand that, okay, your user is trying to, the first thing is the name of a program which you're trying to invoke, WC. The rest are the arguments, right? So the shell itself will start a new program, a new process, WC. We will talk about how to start a new process, passes those arguments -L and ls.c to this new program, because shell doesn't know what to do with this -L and ls.c, but WC does, and so it's the arguments for WC, right? And essentially, WC starts running as a new process, sends it output to the standard output, for example. Maybe it's a console, which goes to the terminal, which like essentially gets printed on your screen, and then it exits with an exit system call, saying, okay, I'm done. And maybe shell says, I'm going to be waiting for this child process, which I created to be done, just because when it's done, I'm ready to start, like, take a new command, and maybe I'll type some, the user will, like, shell will output this command prompt, and the user will type something new here, trying to execute a new command. Yeah.
When you mentioned shell is like an interface, do you mean that like the shell is kind of responsible for issuing the interrupts and stuff?
No. Shell is a regular process, no additional privileges. Shell uses system calls, not interrupts, nothing. So only what system calls allow you to do. That's what you can use in a shell. That's why I'm saying your homework will be to program a shell, which means that I'm not going to let you to change the kernel. And there are multiple shells which are more powerful, implement more powerful language here. You can implement a shell which maybe understands the whole Python. Why not? Like, you can compute anything, and then it will break down the computation into maybe individual programs and maybe run them somehow. And then again, right? So it's just a program. But so yeah, so interrupts are underneath, and you will understand very well how it works. So don't worry. But it's a good question, though. I agree with this. Any other questions? What WC does? Wait is a system call which allows the shell to wait, or a program to wait for a child to finish. So essentially, it's to support the following functionality, because if you don't wait and you output this command prompt, and ls is still outputting like whatever list of files, this will be overwritten, right? And in the end, you will just end up with some name of a file at the end, and you don't even know, user doesn't even know, like, is it over or not, because maybe it's just delayed, right? So that's the primary use case, essentially wait for the child to finish. Okay. Anything else? But it's a system call. Everything what I type actually here was this through type font exit, wait. Those are the system calls, right? Okay, so we notice that we need to access files. So let's start with files because it's easy to understand and they're kind of form the core of this interface. So an open is a system call which takes the name of a file plus some additional arguments, kind of like maybe I want to open a file as in a read-only mode, or maybe read-write or something like that, right? And returns a file descriptor, right? So if I ask you a question, what is this file descriptor? Do you know? It's a pointer in memory. It's a number. Yeah, it's a number. And this is what this number means. So again, green is a memory of your process. Yellow is the memory of a kernel. Open returns a number, which is an index into a table. So in effect, it's a pointer. I just wanted to emphasize that it's a number. So the kernel maintains a table, which is called a process file descriptor table for each of the processes, right? Initially, this table is empty. Or maybe when the process is created, like a couple of those entries for standard input, output, and standard error are created, right? But the rest of the array or the table are empty. And when you do an open and you say this is a file, the operating system goes into the file system like subsystem and says, okay, create me a file. And if the file descriptor which you get is number 3 in this example, right? This is index 3 into this table, and this one will contain a pointer into a file. And this file, then later you can read and write, or maybe it's a pipe, and you can also send bytes into this pipe and read from that pipe as well, right? So, but file descriptor is a number, which is an index into this file descriptor array, right? Not super hard, but it's kind of important how it works. Again, everything is very, very simple, and it, like in this kernel. So the table maintains pointers to file objects, kind of like a object programming language when we hide potentially different functionality behind a single interface. So here you can read, write, not just a file, but will be able to write devices like console. You'll be able to write pipes and files, right, in this kernel. Okay, and the process can get new file descriptors by opening a file, creating a directory. I'm not sure, actually. Opening a device like a console, creating a pipe, or even duplicating an existing file descriptor, right? So you can have multiple entries in this array pointing to the same file. You will see why it's important in a second. Okay, so the moment you did open, you can read and write. So read takes a file descriptor, which was previously open, right? In our example, it was maybe 3, takes a pointer to a user memory where the operating system will copy the content of a file, right? So it's a buffer in memory, and it takes a size of this buffer n, right? And it will read n bytes from the file descriptor into a buffer. It's kind of, okay, sure, you open a file, you say from this position, originally typically 0, will read n bytes, right, into that buffer. And you have to pre-allocate this memory. If you say, okay, read more, then read will fail, right? If you say read less, it's okay, read will succeed, and it will tell you, okay, half of this buffer is maybe filled with data. And similar write, so essentially you say file descriptor, a buffer which contains the data in user memory, and the size of a buffer. So this is how you read and write files. Oh, not hard. So how does it work in case of multiple processes? Just wanted to be concrete for you. So as I said, this file descriptor table will be maintained for each process. So each of them will have 0, and it will point somewhere, but it might point to different things, right? So 2 processes, 2 tables can point to 2 different things, right? And it can happen that they actually point to the same thing. Multiple processes can read the same file or can read the same pipe and write into the same pipe, right? But again, just to make sure we understand. So then how do you think console works? So like this letters which we see, or like which you see, which I can say you see on the screen, but really you see on the shell, right? So it goes to your screen in a way, or if it's a remote terminal, it goes, there was this thing like this, it goes to the serial line and or through a terminal, there's this abstraction, but essentially you can see the letters. So how does it work? So who can tell me? That's the answer. So essentially you can also, as I said, it doesn't always have to be strictly a file. It can be a device. And the operating system will just have a separate mechanism to say, if you read or write into something what is not a file, but a device, there will be some device driver, which eventually, remember this Hello World demo, which we did, will output those letters on the screen and you can read them, right? And we'll vice versa, we'll be able to read from those, from the terminal, from the keyboard, and essentially we'll pass those letters into the program, right? And so the point here is that you not always, so device drivers are also pretend to be files in this paradigm then, in which everything is a file, right? Let me just go back and talk about this convention. So essentially, when you start a program, you ideally want the program to be able to print something on a screen, right? And normally when shell starts a program, it already connects those entries. So entry number 0, file descriptor 0, will be connected to the standard input, which is typically a keyboard, right? Because this is where user wants to like physically type and just send data to the program. One will be connected to standard output, which in most cases is this console, right? Because you want to see the output, but it can be also a file, so it can be changed. And 2 will be a standard error, right? That's the convention. Those numbers are still just a convention, but it will help you because you say, I'm a developer, I wrote a program, I assume that I'm connected to some meaningful input, and you will start reading from standard input, which is file descriptor 0, right? And the operating system plays along and says, okay, yeah, I connect you to something meaningful, but it will be a keyboard, right? Okay. So this is my diagram here. So 0 and 1 typically connected to console and a keyboard, right? Because that's the most common case from where you get the input. This is an example program. So this is the first time I mentioned the source code in this class, right? But it will be more of it. So this is a real cat. Does anyone know what cat is doing? Cat is actually like totally, say again? Concatenate? I would say so, but let me show you a live demo of cat. Let me switch to something like projects with 6. I have many versions public. And cat is like here on my Linux, right? So if I say ls and it shows me all the files in this folder, and we say something like, which one do you like? asm.h. If I do cat asm.h, it actually outputs asm.h on the screen, right? So cat actually reads from the standard input or from the input which is provided. In my example, I set it from asm.h and prints it on a screen, right? So, and this is the actual implementation of this program, which is much simpler than you might be guessing. So it says an infinite loop. It reads from standard input, right? It has a 512 byte file buffer, right? It says, okay, I will read 512 bytes at a time. If I read nothing, that's the end of it. It's the end of the file, right? So we will break and you can exit. If you read less than 0, it means that we returned an error code, and maybe you're reading this input is no longer valid. Maybe someone provided a file name as an input, but it didn't work. You say read error, maybe something else can go wrong. However, if everything is fine and you read between 0 and some positive integer, you just write to the standard output, right? You say, I read something here, I read n bytes, so I will print them out, right? If this can fail, and then you say write error and you exit, right? But essentially, this is the implementation of a cat. And you say, okay, so who cares about it? But again, remember that guy who was standing in front of a terminal, remember, it was a printer essentially. He says, okay, I want to see what's inside my cat mmu.h file, and that's what he does. So that's his very first useful command maybe, right? So shell itself doesn't print anything on the screen. Shell just executes cat. Cat is a command, which you think, okay, like it's a part of your execution runtime, which you can invoke and it will do something useful. If you want to count the number of lines inside the mmu.h, you invoke wc, like lines specifically will do with -l, right? So like that, right?
Yeah, but the actual cat can read multiple files and attach them.
You mean like modern cats, like on Linux?
Yeah.
There are ways to add to the file, like cat. Okay, let's go. Let's take it offline, and then we'll get to this question: how you can copy something from one file into another, or how you can concatenate with a cat. Great. Man, cat will tell you. Oh, man, cat. It can, right? You're right, but let's get to it in a second. Right, but essentially, my point here that is this very simple interface of reading, writing file, C language, and a shell allows you to build those simple programs in which you can, from which you can build an ecosystem, which is useful, right? That's my point today. Okay, cat. Any questions about the cat source code? Okay, good. Let's keep going. So, question is, how do we create processes? I mentioned that we need an interface for that, right? So who knows how we create processes on Unix systems? What are the system calls? Fork, exactly. So what does fork do? Do you know?
It's supposed to process and do, so you have two products. It's basically a function you call once and return twice.
Let me explain what your classmate is saying. So fork is a system call. Imagine you're running a process, something like a shell. Imagine you execute a fork system call. The magic which fork does, it clones the process, meaning it creates an identical copy of a shell. This is the shell which invoked the fork. Maybe you had some variable a, and maybe it was equal to 55. The same variable will be here, and it will also be equal to 55. It's the same memory, kind of. They evolve differently. If you write 56 here in this version of a shell of this process, then this 55 is not affected. It's a private copy, right? But initially, when the fork returns, they are identical. The only difference, however, is that inside the parent, fork returns the process ID of a child. So if this child has process ID 32, the parent will get this process ID. So for example, it can later kill it or wait on it. And inside the child, fork returns 0, right? The question is, I said, we need a way to create processes. This blindly copies the process, but doesn't create anything useful. So what is missing? Okay. Exactly. So Unix has another system call, which is called exec. That's my example of a fork. Again, sorry, I jumped to exec, but let's take a look at this fork example. So here, I invoke a fork system call. It returns me a process ID, which is an integer. If process ID is greater than 0, it means that it's a parent, and I just print here, I'm a parent and my child process ID is such and such. And then I wait for a parent to finish, right? And then I can print child is done. If I'm inside the child, my process ID will be 0. I can print I'm a child, and I can exit with an exit system call, get another system call which allows you to terminate execution of a program. If you get something negative, it means that maybe the system ran out of memory and fork failed, right? And you say it's a fork error, right? Let's get back to the exec, right? So exec replaces memory of a program with a new one, meaning, so if you fork a child, inside the child, you can say something like bin echo, and the memory of this child will be replaced with the memory of the echo program, right? In initial state, like the memory of a child will be gone, but it will be replaced with the memory of this process, right? So in this specific example, if I replace my own memory with the bin echo, will this line ever be printed? no under normal conditions. If exec succeeds, right, exec can fail. And then I print exec error. But normally this line will never execute, because if I replace the memory of a program, there will be absolutely new set of instructions with its new main, right? And the operating system, and it will be a main of this bin echo program, and the operating system will start executing the program from the beginning. I say from main, it's not really true, but close to main, right? With some prologue, right? It's a little bit weird, and I agree. When I first saw it as a child, I also think, okay, man, like it doesn't make sense, right? So this is how this is how shell creates WC, for example, right? It says, okay, first fork itself inside the child. Since it's a child and it's not an error code, it says, okay, I know that I have 2 copies, and I will replace this with the memory of WC, and then WC will start running here, right? It's a little unusual, and I will explain why it's done in a second, right? So this memory gets replaced with the main of WC, starts executing from main, right? So it's a two-step process. First, clone itself with a fork, and then exec replace whole memory, right? So does anyone know why this design choice was made? Apparently, one could argue, why not to do something like create a process like Windows does, and just say, here's a name, /bin/WC, and a new process gets fired up and starts running, right? Which is WC, because apparently this is what's happening in my example, right? But there is something else which can happen, which I didn't cover yet. But what is this other thing? So why they decided that this fork and exec is a useful thing?
So like exception handling type of thing, like you make the copy version then try, you can fall back to it doesn't work for whatever reason.
Not really. But I like your kind of interesting line of thought. It's kind of like create a container, run it. If it fails, well, do something else. Yeah. Yeah.
Okay.
Yeah.
You can do some things with the standard in and standard out.
Exactly.
Types.
Right. So what your classmate is saying, that you have this window of time, you fork itself, the shell is still running, it's not yet WC, and it can change the environment, and specifically it can do something like change the standard input and standard output to implement something what is called IO redirection. And then WC will start running with default values of 0 and 1, pointing not to the, for example, terminal, but maybe pointing to files, right? So, okay, let me illustrate this idea. So IO redirection, that's a powerful mechanism, especially, back in the days, it's been like, what is it, almost 60 years ago, right? Like, what was it, late 70s, so 50 years, right? So imagine we have this, my favorite example, word count application WC, which outputs the number of lines inside a file, ls.c. What? So we invoke it like that, WC minus L, ls.c, it outputs something on the screen, right? But what if we want to output this into a file? How would you do this? Like, you want this to be saved in a file.
Command the pipe and then write the file.
Yeah, you're too quick. Maybe you took this class before, but I wanted to illustrate it with, on Windows, you would say, well, here's another flag, -O stands for output. It will take a file name, which is a foobar.txt, right? That's how you do it on Windows, I think, right? If I remember correctly. So essentially you say, like, let's introduce an extra argument to a program, which will output something to a file. But those guys decided that it's a little bit cumbersome. And instead of doing this thing, they say, how about we will, at the level of a shell, we will support this symbol, right? Which will mean for the shell to say, please redirect the output of this command into this thing. This thing can be also different, but in this specific thing, it's a file name. So the shell, remember, shell is kind of like a language. Think of it as a very primitive Python, free Python, or twice free. And it says, okay, it will parse this command line, will detect this symbol and say, okay, this is a command, this is an IO redirection thing, and this is where the output should be going, right? That becomes interesting because that allows you a certain level of composability. So imagine you can support multiple symbols. So redirect output and redirect input. right? So you can write commands which redirect something into a file, right? So this cat, for example, it's effectively a way to copy ls.c into ls-new C, right? Just because you say redirect everything what you read into this new file. And the same you can say WC will be, instead of like providing explicitly this ls.c, I can say, okay, please redirect standard input to be taken from ls.c file, right? Or in case of a cat, redirect input from ls.c as well. And you can redirect both. So here you can redirect the input from ls.c with this symbol, and you can redirect the output into a different file as well, right? So again, remember the guy was a terminal. For him, it was convenient. It's convenient for me as well, and for you arguably as well, if you learn how to do these tricks. So essentially, you trade this for essentially for this kind of programmability at the level of a shell. So here we have an example in which you say, if you redirect standard input, and standard output into a file, it can be the same file, can be, in most cases, it's two different files, right? Sorry, trying to like right here, right? Those entries in the file descriptor table, entries 0 and 1 will be pointing to different objects in a kernel. So when I say an object, it's a data structure, but it has certain semantics. Maybe it used to be a console, and when you try to invoke a read method on the console, it will go to a device driver and will show up on a screen. If you do a read or write rather on a file, then it will be written into a file, right? Okay, so it allows you to essentially, at the level of a command prompt, program various things. So here's a couple of examples. And it can be done like no changes to the cat program, right? The cat stays the same. It doesn't know when it starts, it doesn't really know where 0 is pointing to. Maybe it points to a file, maybe it points to a console, right? But here's a couple of those examples which try to motivate it a little bit more. So imagine we want to see how many strings are in ls.c, or how many strings, sorry, contain a substring main, right? Normally, you know, okay, how would you do this? Okay, any design strategies for how to build this?
Have a program that finds the string main and a set, and then type that into the program output.
Correct. You know the solution. That's good. Let me just go over it step by step for everyone, right? So imagine those guys who were programming this PDT-11. They said, okay, not only we will build cat program, we'll build a program which is called a grab. And grab essentially filters the strings which match a pattern. So maybe it will match a pattern of main, right? So for example, something like grab string main in ls.c will only one string, right? Because it's the only string in this ls.c which contains the main substring, right? You can like use this input redirection to make sure that it runs. You can also say, okay, how many strings contain a specific pattern? So you say, I have a grep already, which filters the strings. I have a WC minus L, which counts the strings. The question, can you combine them? So what is missing to make sure that we can combine those two programs, right? And the answer, which is what your classmate just said, let's introduce a notion of a pipe, to essentially an idea that you can redirect output of one program into as an input for another, right? So what we want to write is something like that. So we say, please redirect output of a cat ls.c into grab main with this symbol, which is supported at the level of a shell, which is called a pipe, right? Essentially, it allows you to connect the two. So in a way that like cat is running here, redirects everything into grab. This is cat. This is grab. And you can, again, I cannot, like, I'll fix this, but today my writing doesn't work for me. But you can imagine that if you have a collection of the simple programs, maybe something can even like add some numbers for you, right? you can combine them into something more powerful out of a simple component. So like shell again is a tiny programming language. So what happens here? So cat outputs ls.c to its standard output. Operating system somehow implements this pipe, and the grab reads from that pipe and essentially does its own functionality. It filters the substrings which have filters the strings which have substring main, right? A pipe is a mechanism for interprocess communication. When I say interprocess communication, it means that two processes which are completely independent, cat and grab, they don't know anything about each other, but they somehow can send data to each other, right? And this is through this mechanism of a pipe. Let's understand how it works. So a pipe is a thing which is implemented in the kernel. At a very later in the class, we will take a look at the source code which implements pipe, and we'll see which synchronization mechanisms have to be in place to make sure that everything is working correctly. But at a high level, what happens is the following. We have two programs, this cat, which has file descriptor 3, which is connected to an object in the kernel, which is a pipe. And when it writes something into a pipe has an internal buffer here. I don't know what size. Let's say, it varies from operating system to operating system. I think inside x86, it's actually 512 bytes, right? So it can keep at max 512 bytes, right? But if you write, for example, 5 bytes, so you have a buffer which points somewhere over here. It contains maybe a string hello. It has a size 5. Those 5 bytes, like H, E, and so on, will be written into this buffer inside the kernel temporarily, right? And the other program, which is grab with the main argument, can read from this pipe, meaning that one of the file descriptors, it can be 3 as well, but maybe it's different one, points to the same pipe. And what happens is when you read, essentially you provide a buffer. Originally it's empty. You say how many bytes you want to read. Maybe you say 64 bytes. You go into the kernel. The pipe keeps track of how many bytes it has available right now. It reads those hello bytes, how many you wrote, maybe 6. And essentially at this point, it returns that 6 bytes were read. And this buffer gets cleared here. So it's again has full capacity of 512. And this user has the string hello. So essentially one program kind of sent some bytes to another program, right? Any questions?
Wait,
Sorry, go ahead.
there's 2 programs that both share the read end of a pipe.
Yeah.
What happens if they both read? Do they alternate between which data they get, or do they both?
Whoever gets it first wins. It's a little bit unusual, right? So, but the semantics, I don't think it's defined. And you say, if you suddenly, this program, there is no contract that it doesn't have a read end of the pipe. So this program can also read. And which program invokes read the first? The operating system itself has a synchronization mechanism in place saying that whoever gets it first will read it, right? Atomically. It will read those bytes and the other program will get nothing.
Somebody told me that it was based on how you write it in, so whatever's first will get it first, and then it will type whatever it finishes to the next project or process, and then it'll compute that way.
Yeah. But wait, I think what you're trying to make is another point about what happens if you have 3 programs, for example, connected with 2 pipes, and which programs runs first. And yes, you're right, there is no defined order. So, there is no defined order between these 2. So maybe you even started cat first, but the scheduling algorithm inside the operating system somehow chose to run grab first. What happens then? That's a great question, actually. Grab says, okay, read me something. The pipe is empty. Grab returns with 0 bytes. Hopefully the grab is smart enough that until it receives an error from a pipe, it will continue in a loop reading it again. And eventually the cat will start running, and maybe it will write hello, and then grab will pick up this hello, but maybe grab will write twice something like hello, and they will do another write world. And an interesting part, which actually is the most interesting part, is what if this ls is larger than 512? So maybe what if it's a megabyte? Then what? At some point, the writing, and maybe sometimes maybe they run almost at the same speed, and you write a little bit, you clear the pipe, it's empty again. But maybe this cat gets ahead and just fills in the entire pipe here. Pipe has only finite memory here. And at this point, the write into a pipe will return an error. Not an error, it will return that 0 bytes are written. And then again, your correct logic of your cat would be to keep trying to write again. And then at some point, grep, which runs like concurrently, will be switched in, will get a chance to read something from a pipe, will clear some of the pipe's memory, and will make sure that, you know, cat can go ahead, and eventually then they will go through the entire megabyte, right? Another question.
What happens if you use an output redirection instead of a pipe?
Output redirection doesn't connect a program, so it connects the static object like a file or a device, right? So it's a little bit different. So the question is why? Why did they chose to introduce these 3 different symbols? Because input and output redirection explicitly this allows you to choose what you're redirecting, input or output. And here, depending on whether you're the left side of a pipe or the right side of a pipe, you either redirect input or output, right? That's the logic of this language. I'm not saying that that's the only way you can build it. So you can build a super pipe, which allows you to do something else, right? Like a T is a good example, which maybe allows you to redirect into 2 different outputs, something like that. But they were trying to optimize for the common case, and they tried to come up with the minimal set of primitives which were making the system usable and still keeping it minimal, right? Okay, so we got the idea of a pipe. So pipes allow us to connect programs, right? So connect output of one program to the input of another. So the question is really, what did we achieve? So as again, like I was saying, you achieve this, it's a language really. So you can, out of the simple components, you can do something useful. So if you want to see how many strings in ls.c contain main, so it's almost like an SQL query at this point, right? So you say, I will cat the entire file ls.c, I will filter the strings which contain main, and I will use word count to count them. So it should output 1. If you want to count the strings which contain letter A, the only change which you do, instead of this main, you type A here, and suddenly you have 33 lines which contain A, right? So that's, you know, back in the days, you didn't have an SQL engine or your whatever spreadsheet. That was cute. The people were building those complex pipelines out of simple components, right? Today, you do that the same in a data center. You say, well, I have AWS, it provides me with some like primitives like queues and whatnot. I actually am not a big expert on that, but then I will run my video processing and, you know, unlimited storage, everything is virtual, elastic, but same idea, redirect input of one into output of one into input of another. We had a question there.
That's fine. Create a memory clone of the, let's say the product, it's a cat, there's a cat and the file size is too big. So does it create a memory clone? Because that would result in a slowdown of, let's say, the file size.
No, pipe, remember my picture here. Pipe is a thing which is implemented by the kernel. And inside your kernel, in x86, it will have only limited capacity, literally 512 bytes for buffering. If you want to pipe a megabyte through this 512, you will have to do so many iterations, right? So divide one by another, and there is some concurrency. They don't always perfectly run one after another, scheduled by the operating system. So sometimes you may be able to run 1 byte because the other guy just read 1 byte. So although you have 512 bytes cached, right? But that's it, right? The whole megabyte will be sitting here. There will be a file object from which this is the file object from which ls. This is like through the hierarchy of a file system will be connected to a disk which contains the ls.c, right? And you will be reading like some number of bytes each time and then writing them into a pipe and so on until you go through the entire file, right? No more memory will be allocated. Besides that, yeah, besides the buffer, which you will use here to read something from a file into this buffer and maybe write from this buffer into a pipe, right? The buffer can be small, can be 64 bytes, for example.
Some mechanism here, in next missing.
Okay,
For the pipes memory, I don't know.
no, this is inside the kernel, right? So when the kernel creates a pipe, it will allocate memory for this 512 bytes. But that's the old memory which gets allocated, plus the pipe data structure itself. Right? Any other questions? Yeah.
Is 512 fixed or it depends on OS?
Depends on the operating system. I think Linux by default has something like 64 kilobytes.
So it's adjustable?
In Linux, it's adjustable, I think. I'm not entirely sure, but most likely. In x86, it's just a compile time variable. You can change it at compile time. Is there a limit? Oh, that's a good exam question. Actually, I think I used to ask something. There is no limit per se, but at some point, shell will run out of, like, the system will run out of memory. So if you try to, it's something what is called a fork bomb, right? So it's a program which in a loop keeps forking itself, exhausting system's memory because it's a legal behavior. So you can fork itself, right? And the question is like, how many times you can fork itself? I used to ask this question on the exam towards the midterm. I will ask you to, guys, please count how many pages are wasted every time you create a new process, and you will be able to count, don't worry. And that's how many times you can fork. And so that's the limit essentially. So, but shell itself, I don't think, I mean, maybe some, first of all, there is no single implementation of a shell, right? And maybe some shell says, okay, the string is too long, so you will not be able to fit pipe so many times, but normally there is no limitation. So you can type very, very long string. And any other questions? Yeah.
Does the operating system also manage it? So like, I gotta write like 6 something about like.
Hold on, I missed the beginning of the statement.
Does the operating system track file descriptors open or not? Like, if I try to type file descriptor 6,
There is no even way to open file descriptor 6 twice. So open doesn't allow you to choose a file descriptor, right? In x86 and some other operating systems you can, and then you will fail. You're right. But in this interface, you don't have a choice. And I will explain the convention which allows you to close a file descriptor, and then the open will choose the lowest number which is available. And sometimes you use this convention to say, I want to replace 0 with something to you. So you close 0 and you open right away. And this way the operating system chooses 0 because 0 is the lowest number which is unused in the file descriptor table. It will be probably there next time. Okay. So we looked at this composability, right? The question is that, okay, is it convincing story? I was kind of arguing that it's better than the solution which Windows used to provide you, because at some point people say, okay, we have graphical user interfaces. They're so powerful, we can put as many letters as we want on the screen, right? And this is specifically, I found the grab program on Windows, which allows you to like specify a ton of nonsensical like parameters. Maybe it's not the best example, but the high level story here is that instead of customizing the programs to do all what you want, maybe a better strategy is to come up with some smaller subset of core primitives and a mechanism which allows you to combine them, right? So that's the point, that the IO redirection is a powerful mechanism which allows you to do that, right? So like say, okay, this specific string, how many times, or maybe a different string, or maybe you can even count them, right? So let's stop here probably, and we'll continue with explaining how IO redirection is built next time on Thursday. We'll finish the IO redirection and we'll go with the next topic. Thank you.
I looked at the name, I didn't say
Let me just stop the recording.
Yeah, no, I